Hello, I'm Dr. Migler, and I'm an assistant professor in the Computer Science and Software Engineering Department. And my student, Ryan Solorzano, has been doing excellent work for his master's thesis. And it's a nice follow-up to Dr. Fernsler's presentation because we're using contact networks, and Ryan is slightly modified the SIR model. And he's going to talk about the impact of just testing and quarantining, and what testing and quarantining, what sort of outcomes we expect with that. So Ryan, please go ahead.
Sure. Let me go ahead and share my screen then. Okay, and I'm assuming that should be visible, so just let me know otherwise. So yeah, my name is Ryan Solorzano. I'm a master's student in computer science, and we'll be talking about monitoring the spread of COVID-19 over varied contact networks. So like we said, we focus more on testing rather than simulation, and just kind of seeing which testing strategies are the most effective. So a quick overview of contact networks. Contact networks, the vertices can represent organisms, and two organisms can be connected if they come into contact in a way to allow spreading of the disease. So this can be dolphins or, of course, people. So in the case of our research with COVID-19, the vertices are, of course, people, and two people can stay connected if they breathe that same air to allow transmission of COVID-19. So here's an example contact network. We can say like maybe A, B, and C are all roommates, and so that's why they're all interconnected. And then maybe E has a class with C, and that's why they're only connected with C and not with B and A. And let's say maybe D is a club sport with B and C, but not A. And then we can also introduce this idea of a temporal graph, where basically maybe at night, A, B, and C are connected, but E and D are not. And then again, like maybe during the day, during club sport time, B, C, and D are connected, but not A and E, and so on. So this is kind of the overall idea of contact networks. So the collaboration we used was from a collaboration called SocioPattern. So SocioPatterns is a collaboration between researchers and developers around the world to collect this contact network data and like build these networks. And so we use 5 different contact networks from these SocioPatterns. 2 are actually office workplaces, 2 collected 2 years apart, and 1 is collected from a high school, another is from an elementary school, and another is from an academic conference. And I'll get into a little bit of the validity of this, but then in all 5 contact networks, 2 people are connected if they come into 1.5 meters of each other, or about 5 feet for a 20-second period, and they all use the same infrastructure to collect this data. And we could accept this to be a reasonable approximation, breathing the same air for 5 feet. And we use, and this list content networks collected using RFID tags. So if anyone's it's done like a 5K with like a racing number, they have like a chip on the back to collect when you finish, that's an RFID tag. And so it's the same technology. And let's talk a little bit about the model we use. So we have this SEIRQ model where each person in the network can be in one of 5 possible states. And that's susceptible, exposed, infectious, removed, and quarantined. You notice I changed it from recovered to removed, and that's just because it encompasses all possible outcomes of the disease. So basically, everyone starts out in their model. Every vertice starts out with susceptible, and then to start the outbreak, we move 1 to infectious. This can vary based on simulations, but in ours, we chose to use 1, and we changed the person to be infected every time. And then in the content network, we basically just play out the data. And if someone in infectious comes in contact with someone susceptible, you have a certain amount of chance. For us, we use 3%, which we kind of tweaked based off of research we had. But basically, there's 3% chance to be moved into this exposed bucket, which basically guarantees that you will eventually contract the disease. And again, infectious after a while, let's say it varied again on research, but somewhere between a week or 2 you can be infectious and then eventually be moved to removed, and then again exposed, you're exposed for a little bit of time, and you have some sort of chance of you eventually move to infectious, and at any point we also have our testing strategies. So basically our testing strategies test anyone in this network and you have some chance of testing positive based off if you're exposed to infectious, again, based off of research on these tests. And then you can move to quarantine. And an important part of this is that we assume a perfect quarantine, meaning that they're completely removed from the simulation. So like no contacts can possibly happen. And after the 2-week period, you can be removed. And then we also include the possibility of a false positive test, moving from susceptible to quarantine, and then after that 2-week period, moving back to susceptible. So talking a bit about our testing strategies, we have the easy one where you don't test anyone, basically just seeing what happens with our outbreak. And this can be considered our control. And then we have random batch testing. So this is also a bit of a naive approach where you basically just get a subset of the population, the size of which depends on the number of tests we have available for that day, and then just test them and quarantine them appropriately. And then we have individual testing. So this is a bit inspired by what we're doing at Cal Poly. We're basically, again, developing an availability test. Every single person is regularly tested. So let's say a person can be tested every 3 days, for example. And again, the amount that person is tested is depending on availability of tests. And then we have testing using degrees. So this is a little bit more graph approach or graph theory approach, where basically degree of a person is how many people they've come into contact with the previous day. And so the higher degree you have, the more likely it is to be a super spreader, because you, one, have a lot more chances to be contract the disease, but also two, the more important part is that you have a lot of chances to spread that disease. And so the idea is hopefully if we identify these people early on, we can mitigate the spread a lot quicker. And let's get a little bit to our results. So this is results from our high school network. Again, so to be clear, the vertices represent students and teachers, and the edges are just whenever they interact. And this is a content network of about 326 individuals. And again, we assume perfect quarantine, so that would just mean that they don't go to school for 2 weeks. And then again, this is collected over a 2-week period. And but our simulations ran for several weeks. And so whenever we ran out of data, we just loop the data, which is a very reasonable assumption to make, especially in a high school setting where people are creatures of habit, people have the same schedules, meet with the same people, same friend group, so on. And so that's what we do here. And let's look a little bit about one more note. We also don't assume any sort of behavior change, such as mask wearing or social distancing or making pods within classrooms. And that's just because we want to see just purely just the tests. And so again, this graph on the x-axis, we have the number of tests per day going from 0 all the way to the entire population per day. And then we have on the y-axis the maximum number of people infected in our simulation. So if the infectious bucket had like a graph of number of people, it is eventually going to peak at some point and then go down. And so the peak is what we plot here. And each plot point here represents 10 simulations averaged out. And so that we have like a very clear outcome. And so this red dot here represents no tests. It's about 160 people peak infection. And then strategy 1, the random batch testing, that follows this nice little curve all the way down. And strategy 2, the random individual testing, interesting enough, is kind of hard to distinguish from the first one, where basically there's not too much of a difference if you just get a random batch of the population versus if you get if you guarantee that every single person is tested. And so that's very interesting. And then strategy 3, if you look at this, it seems to do a little bit better until about halfway, where it just kind of becomes random noise of who becomes better. But generally with first like half, it seems to perform better than the first two. And this is actually very interesting and actually very good that we see this, and we're happy with these results. And then here's what this looks like at an office workplace. Very similar, just a little bit more sparse because the network is smaller. And then at an academic conference. And this academic conference was collected over a period of 2 days. And so maybe not necessarily realistic to loop those over for weeks and weeks. However, it's important to note that academic conference had a lot more dense of a network. And so we can see that the degree became a lot more important early on than the other strategies. And so that's just reflected by the density of the network. So some future work really quick. So basically any future work can improve the realism of the simulations and strategies. So one point is the asymptomatic and symptomatic buckets. We have proved that asymptomatic people can still spread the disease. However, we didn't necessarily take that into account. And also you could just test symptomatic people and so on. You can also look at contact networks where strength of the signal is indicated. So you can kind of vary that infection probability. Strategy with perfect contact tracing would be interesting. And then a combined graph theory strategy. And then something I didn't mention here that I didn't know about is something we saw with the particle simulations with the different, just different simulations like altogether. And then also simulations involving 2 doses of vaccines with varying efficacy could be interesting, so that you could target the right population and stop the spread of the disease. And then combining content networks to make a community would be very interesting, such as like, let's say you have a workplace and a preschool and you make like families within that unit, and just to make it more realistic and more granular, to make like a very like realistic community could be interesting. So here's some of our references really quick, and then that would be a good time for questions.
Thank you, Ryan. Wow, that was a great presentation. And what you made, just of note, those graphs and figures are really well designed. And we know there's a lot of data points in there, and it took a lot of work to do that. So we have a few minutes for some questions or comments. Dr. Fernfloor, yes.
I have a question. Yeah, so yeah, really great work. And I love that, because this is like on the other end, like exploring sort of the heterogeneity, you know, kind of diseases, which is the opposite thing of what I'm doing, which I'm really, it's really cool. So it's just, I was wondering, is there a simple prediction for you know, your outcomes based on like the network density? I mean, can you sort of, is there a simple model that describes like, you know, how testing would behave? Because you said like the faculty network, you simulated one network density, and then the high school, a different one.
Yeah, that's actually a really interesting question. And like you saw, like that curve was seemed pretty smooth. And so we can actually look into that while we're still like collaborating all of our research. And so this is actually like that research, or the results were very recent. And so that's actually very interesting to look at, but it seems possible, right? Like it seems like there was a distinctly the more dense networks did better. And so that's something we can look into.
Cool, thanks. Yeah, great work.
Thank you.
And one thing to note is that the networks that Ryan the networks he was using were actually they were much denser than you would expect a real life network to be, because as he alluded to in the future work section, these are small, super interconnected networks within the larger network. And so there was a lot of density that if you considered a whole, you know, community, a whole city, the density would go way, way down. So